Day, and it's a great day for mathematics as always. Today we are talking about quadratic equations. What's quadratic? Well, quadratic equation is of the form ax squared plus bx plus c equals 0. A, b, and c are constants, and a can't be equal to 0. Quadratic function is the same form. It's just that we set this form equal to y and not equal to 0. Remember that y could also be f of x equals all of that. Remember, we use f of x for function notation, and it replaces y. Now, what makes a quadratic is this guy right here. The greatest exponent to any variable is 2. That makes a quadratic. So any equation that has a exponent of 2, like 2x squared minus 3 equal to 2x, that's a quadratic equation. It's just not in the form there. I could put it in that form real quick. 2x squared minus 2x minus 3 equals 0. And then it's in this fancy-dancy form, but they're both quadratics. It's the same equation, just looks a little different. Quadratics are, of course, polynomials, and here's 4 of our more famous polynomials, and they're just named by the greatest exponent. Linear, or they're classified by that. Linear, the variable has an exponent of 1. Quadratic, the greatest exponent is 2 for a variable, and on down the line. I think you get the picture there. One famous scientist who did work with quadratics is our friend Galileo, and what he found out was that projectiles, their path, the path of any projectile travels in its path is parabolic. In other words, it travels in the shape of a parabola. And the graph of a quadratic is a parabola, so therefore he could model projectiles, or the flight of projectiles, using quadratics. So in tribute to our friend Galileo, we are going to get a groove on just to get this party started. He's a bad man. Galileo in the house. I point my telescope in the air sometimes, singing, "Ayo, it's Galileo." Alright, that's ridiculous. I apologize for that. Nobody wants to hear that. Okay. So we got to solve these puppies. We can solve quadratics by factorizing, by completing the square, using the quadratic formula, or using technology. We're going to show you all of those. If we factorize, we use the null factor law, which simply says that if I have any two numbers and I'm going to multiply them and they're going to be equal to 0, well, just only one of them has to be 0. For example, 3 times 0 equals 0. If you think of this as the a term and the b term, a is 3, but it doesn't matter because b is 0. So when I multiply them, they become 0. Or 0 could be the a term times 1232. Well, this 1232 is insignificant when we're multiplying because of the null factor law. Only one of them has to be 0 to get a result of 0. This is important that the roots, or the solutions, used interchangeably, of a quadratic are any values of x which satisfy the equation or make it true. Well, what would make this true? What would make this true is if I replace x with something that, after I did the arithmetic, results in a value of 0, or being equal to 0. Okay, so let's solve a real quick. 3x squared plus 5x equals 0. Quick review of factoring. The first thing you check, do terms have anything in common? These have an x in common, so I'm going to factor it out. And all of a sudden, life is just swimming because I can use my null factor law. I have my first term, x, times my second term, 3x plus 5. This is my a term, and this is my b term. If a times b equals 0, then only one of them have to be equal to 0. Either one. So that's why we always do this. Well, x could be equal to 0, and that would make this equation true. Or 3x plus 5 could be equal to 0. So I already have x solved for here. And then if I go ahead and solve for x here, oops, that's a -5. Oops, equals -5/3. And if we replace x with 0, or if we replace x with -5/3, then we would get a true equation. We would get 0 on the left side, which is equal to 0 on the right side. And we can say that x equal to 0, or that 0 and -5/3 our roots are solutions of the equation. Okay, so this guy right here, I need to clean him up a little bit, because in order to get it in a nice form to factorize, I need to get everything on one side of the equation and set the whole thing equal to 0. Otherwise, I can't use the null factor law. And just a quick factoring of a quadratic. You guys know how to do this. This is going to be x, x. I need factors of -6 that combine to give me -5. So that means I'm going to have a -6 and a +1, because -6 times 1 is -6, and -6 plus 1 is -5, which is just a reverse of the FOIL method. In other words, if I FOIL this, I end up with this. And by null factor, x minus 6 could be equal to 0. Again, just real quick, this is my A term, x minus 6, and this is my B term. And again, I have A times B equal to 0. So if either one of them are equal to 0, then we are in business. Here x equals 6, or x plus 1 equals 0, which means x is equal to -1. And I told you we could solve these by graphing. Okay? And I'm going to show you that real quick. But before I show you that, I want you to see that I'm actually going to graph the function y equals x squared minus 5x minus 6, and I'm going to write it as f of x equals all that. And I'm just writing that because that's how it appears on the calculator, and it's in function notation. Galileo back in the house! See ya. Okay, so I have to graph that on my fancy dancy graphing calculator, and that function was x squared minus 5x minus 6. Now I want to know where this guy equals 0. Now I can't see the bottom of them, so I'm going to just change my scale real quick. That really bugs me. To a -20, and I can see the bottom. So again, I'm asking where, I want to know where does this function equal 0? Well, the value of a function corresponds to its y value. And the y value is 0 when the graph intersects the x-axis. So I need to find the zeros of this function. So I'm going to go to Menu. I almost always want to analyze my graph, and I want to find the 0. Oops, yeah. Okay, and it's asking me where's my lower bound. Well, that's on the left side of the intersection of the x-axis. So I click again, and it tells me that that point right there is -1, 0, meaning that the function is equal to 0 when x is equal to -1. And then I have another guy over here, so I'm going to do the same thing again. Find the 0, lower bound left, upper bound to the right, and again the function is equal to 0 when x is equal to 6. And if we go right back here, those are the same solutions that I got. X equals 6, x equals -1. So I solved it graphically with my calculator and using algebra or the null factor law as well. Now if I graphed y equals 3x squared plus 5x, guess where it would intersect the x-axis? Well, it would be a parabola, It would intersect the x-axis at x equals 0 and at x equals negative 5/3. I encourage you to go ahead and graph that on your graphing calculator just to see if I'm lying or not. But I'm not, I promise. Now, these are examples in your book. I'm not gonna do A for time's sake, because you can look back at it, and they're pretty similar. So let's work on B. Go back to blue. So I am going to set this equal to 0 by subtracting 11x and subtracting 10 from both sides of the equation. So then I have minus 11x minus 10 equals 0. Now, I'm going to just do a little scrap work over here. It is a quadratic, so I'm hoping it's going to factor in the product of two binomials. The problem is that if you remember FOIL, this could be 6x and x, because 6x times x is 6x, or it could be 3x and 2x. And then factors of negative 10, negative 1 and negative 1 and 10, negative 2 and 5, or 1 and negative 10, or 2 and negative 5. There's all kinds of combinations that I'd have to try. Well, one thing I can do is I can split the middle term. And the way I do that, how do I split it? I'm going to rewrite it. And to know how I need to rewrite it, I take 6 and multiply it by negative 10, the coefficient of the squared term times the constant, times the c term. And that gives me negative 60. Okay, this is a method you can use. So I need factors of negative 60 that combine to give me negative 11. Well, what are factors of 60? Well, 1 and 60, no. 2 and 30, no. 3 and 20, no. How about 4 and 15? Hooray! Yes. 4 times negative 15 gives me negative 60, and 4 plus negative 15 gives me negative 11. So that allows me to use 4 and negative 15 to rewrite the middle term, and I get, here I'm going to move down here to give me room, 6x squared, and I'm going to say plus 4x minus 15x minus 10 equals 0. And why did I do that? Well, this guy is, or those two guys combined to give me negative 11x. In other words, 4 minus 15 is negative 11. Okay, so, well, why did I do that? Well, let me just rewrite that real quick. 6x squared plus 4x minus 15x minus 10 equals 0. Okay, well, now I'm going to just look at these first two terms and see what they have in common. And they have a 2x in common, so I'm going to factor out a 2x, and I get 3x plus 2. And then I'm going to look at these two terms and see what they have in common. Well, they have a negative 5 in common, and that leaves me with 3x plus 2 equal to 0. Well, now I have a product of two terms here and a product of two terms here, and they both have in common 3x plus 2, which means I can factor that out. And what am I left with? Well, I'm left with the 2x minus 5. So that maybe takes a little bit more time, but you would be guessing and checking a lot here trying to come up with this, and it might take you a little while. That's why I kind of like the splitting the term method. But if you can get here, without doing this, then that's fine too. And then we're back to null factor, easy peasy pumpkin pie. And I solve this, blah, blah, blah. X would equal negative 2/3, or x would equal 5/2. And again, what does that mean? Well, that means if I replace x up here with either one of these, then, and I did my arithmetic, I would get 0. Also, if I graphed the function 6x squared minus 11x minus 10, the parabola, the graph of the quadratic, of that particular quadratic, would intersect the x-axis at negative 2/3 and 5/2. And again, we call these solutions or roots. Okay. You could run into something like this. The thing that's bothering us here is the x in the denominator there. So I would just multiply the whole thing by x to clear the denominator, multiplying each term by x, distributive property. X times 3x is 3x squared. And then times 2 over x, this is the whole reason I do it. The x's cancel using the Capel theorem. Capel as in boom, boom, cross them out. I don't want to cross them out because I still have to take the x times the negative 7. And I have to take the x times this negative 7. That equals negative 7x. And then we get to factor like it's 1999. Okay. And I could do the split the terms thing if I wanted to. 3 times 2 is 6. Factors of 6 that give me 7. That'd be easy, 6 and 1. And I could split the terms. But this isn't so bad because I know that this has to be 3x and x. I know that these have to be positive because my last term is positive and my middle term is positive. And there's only 2 factors of 2, 2 and 1. It's a prime number. And the 2 would have to go here and the 1 would have to go here in order to get 7x in the middle. Using null factor, I set them both equal to 0. And I get x equals negative 1/3 or x equals negative 2. Again, if I replace x in this original equation up here with either one of these, I would get a true statement, or here I would get 0. If I graphed this function on my calculator and found the zeros where the graph intersects the x-axis, that would occur at negative 1/3 on the x-axis and negative 2 on the x-axis. And I think you should do that. I don't want to, in the interest of time, I'm not going to do that, but you know how to crank that into your calculator and find the zeros I showed you before. Okay, I'm going to pause here. We still have to complete the square and use the quadratic, but we're running on 18 minutes, so I'm going to pause and you can watch the next video to learn about completing the square and quadratic formula. See ya!